problem 3.16. Today I'm going to explain how the problem should be solved. First of all, the problem states an experiment was run to determine whether four specific firing temperatures affect the density of a certain type of brick. A completely randomized experiment led to the following data. At first, you can see the data. We will begin this tutorial by showing the process by which the bricks are made and how the firing temperatures affect the process of the bricks.
A 4-foot-high stone wheel with a steel tire grinds the shale into powder. It grinds up to 50 tons of shale per hour. A screen sifts out pieces that need more grinding. The powder goes to the pug mill that mixes it with water. This makes a thick paste that will go through the extrusion machine next. The extruder forces the paste through a rectangular opening to form one long continuous piece called a slug. At the same time, it shaves off the crustier top layer to expose what will become the face of the brick. If this gray shale mixture is fired as is, it will naturally produce a red brick. To engineer a different color, they coat the slug in sand mixed with an oxide mineral such as zinc or iron. Next, they texture the surface with a textured roller. This is just one of many popular designs. Then a large knife comes down like a guillotine and slices the slug into 5-foot lengths. You might be wondering where those 3 holes came from. Well, remember how the paste goes through the extruder to form the slug? Inside are 3 pins. They make 3 holes designed to decrease the brick's weight. Out of each 5-foot length, they cut 23-inch bricks. The ones on the ends are uneven, so they go back into the mix to make new slugs. Next comes the delicate job of stacking these newly minted bricks to be. A machine first separates them. Then, using inflating bags, it grasps them, raises them, then stacks them. Meanwhile, the water in the bricks is starting to evaporate. To hasten that process, the bricks go into a dryer for 2 days. The dryer gets its hot air from the heat generated by the kiln, where the bricks go next for firing. The kiln is really a giant oven. It bakes the bricks at 1900 degrees. One and a half days later, the bricks are ready.
The first problem of this issue starts by asking us to do the analysis of variance. First of all, we must notice that this is an unbalanced case. We can notice this by the yellow blocks where there are no data. So therefore, there is a special way in which we must confront the problem. We also notice that A equals 4 due to the 4 levels, the 4 different temperature levels that we have. We will first start by making the sum of each row, which is the yi dot, and then by doing the y double dot. Once we have this data, we will continue with the analysis of variance table. Our only source is the temperature. The sum of the squares of the temperature of the treatment is as follows on the second equation at the bottom. Although the only thing that we must notice is that 1 over n must go inside the parentheses, the summatory, since the n's are not constant. So for every yi dot, the n is different. So we will do the sum of the squares and then subtract the y double dot squared divided by capital N, which in this case is 18, since there are 18 types of data. After doing the sum of the squares of the treatment, we must then follow by doing the sum of the squares of the total. By this, we must use the first equation that we see below the table of the ANOVA. We must use all the data, do the sum of the squares of all those data, and then subtract the y double dot squared over the total number of data, which is 18 as previously stated. Then we would do the sum of the squares of the error, which is just the difference between the sum of the squares of the total and the sum of the squares of the treatment. Then we will proceed by doing the difference of the degrees of freedom. First, we know that the degrees of freedom of the temperature is A minus 1. As previously stated, A equals 4, so therefore the degrees of freedom is 3. The total is A minus 1, N minus 1, capital N. So in this case, there are 17 degrees of freedom for the total. And once again, the degrees of freedom for the error is the difference between the degrees of freedom of the total and the temperature, which is 14. Now we will proceed with the mean of squares. We must do this by doing the sum of the squares for its respective category by its degrees of freedom. So for example, for the temperature, it's going to be 0.156111 divided by 3. And by the error is going to be 0.36 by 14. Now we will get the F initial, the F test. By doing this, we must use the difference, not the difference, the quotient of the 0.052 divided by 0.0257, which is the quotient of the temperature, or the quotient of the mean of squares of the temperature, or the mean of squares of the error. Then we must use the F test. We know from the instructions that we must use 5% as alpha, so therefore we must use the F of 0.05, 3, which is degrees of freedom of the temperature, and 14, which is the degrees of freedom of the error. This gives us a number of 3.34, and since F0 is not greater than F 0.05, 314, then our criteria is to not reject hypothesis. Therefore, the ANOVA states that the different levels of temperatures do not affect the density of the bricks. We will now proceed to make the multiple comparisons test. We are asked to do Fisher-LSD test. So the first thing we must do is add another column to the original data, which explains the yi dot average. We're going to need this for the Fisher-LSD test. And after this, we must notice that the Fisher-LSD has no increaser, and it uses the t-table. So it is an easy way to start the problem. First of all, we must order the yi dot averages from largest to smallest, and then get the difference from the largest to the smallest. As we notice, y1 is actually the largest, and y2 is actually the smallest. So we get the difference, y1 minus y2, y1 minus y4, y1 minus y3, and the rest of them. As we can see, the differences vary, and then we're gonna compare this to the LSD data, which is actually at the bottom with the two formulas. The first formula is in the case that this wasn't if this was a balanced case. Since it is not a balanced case, we must use the bottom one. So for every pair, we must use the different n's that we have. So that's why every LSD is different than the previous. We must also take into consideration that the T alpha divided by 2 is 0.025, since alpha was was 0.05, and n minus a is actually 17 minus 3, which is 14. So that's the answer we get, 2.145. And after we do the comparison from the difference to the LSD quotient, LSD factor, we get that the labels are the same. The next step in our analysis is doing the residuals. We got the residuals by doing the observed minus expected. The observed value was the actual value we had, and the expected was a y dot average. So once we did this difference, we got another table with the same characteristics as the data table, with two missing values that were the ones that we we didn't get due to the unbalanced test. And in order to test the normality of the distribution, we needed to do what it is a normality paper, a normality graph. In order to do this, we needed to get all the residuals, place them from lowest to highest, as we can see on the sorted residuals table, and then we would give them an order, and the probability will basically be the order minus 0.5 divided by the total number of data, which is 18. So basically, in the next graph, we could see how it does follow a normal distribution. Maybe the type of graph that we used was not the best, since we could see that the very first data at the very left could be something that could be interesting to notice, but it does go with the statement that the analysis of variance had. Then we proceeded with the constant variance test. The way we did this was by doing the residuals that we had and putting them against the expected value. So as we can see on the graph, there may be a problem with the dispersion from the residual from the expected value 21.7. The range is quite big. It may be a problem. So therefore, these are the results. This is everything we learned from chapter 3. Special thanks for everyone who's listening to the video. And here's a reference of the video and where I took it from.